These guys. Well, come to class on time. I'll give you guys a 20-minute break. Where's Nafe? Try to make the class on time, right? Every single class you guys are All right. So we're going to pick up where we left off last class. We're talking about telescopes. And then we're going to move on to using this idea of telescopes to understanding how the human eye works, because it's very, very, very similar. I had this image for you guys last class, and it's quite important, and I want to go over it because there's quite a few important elements here. Here's like a very simplified telescope, right? It's a two-lens telescope, and you guys know that it's very possible to make a two-lens telescope because you actually made them the other day in the chem lab. A few important things to mention is that when things are coming from a really far distance, that they're in parallel. The rays that are coming in are in parallel, right? So you can see here my ray that's coming in from here, here, and here. They're all three parallel. That means I'm watching something that's really far away. That's really different from a microscope because a microscope, the object that I'm looking at is really nearby. What you guys pay attention to is this angle here, right? We call that the objective angle, all right? And that's the angle in which the incident rays come at the objective length. Here is going to be, oops, hold on, a second. All right, here. On the right there is going to be the eyepiece angle, all right? And the bigger the difference between these two angles is, the bigger the magnification is, right? So we can say that the magnification is equal to the ratio of those two angles, all right? But that's not super important because that angle is not going to be always really easy to measure. And there's a much more efficient way to measure magnification. In this case, we have this fantastic equation here, right? And this only works for objects that are really far away. So let's say for a microscope, for example, you would not be able to use this equation. But for objects that are really far away, you can use the equation that the magnification is just a ratio of the two focal lengths, right? So do you remember when we were in the lab the other day, I told you guys to try to take the difference of your two lenses to be as great as possible? The reason for that is because on top you have the objective focal length, and you want that focal length to be as big as possible, and you want your eyepiece to be as little as possible, so you have a big number divided by a small number, so you can have a big magnification. Make sense? All right. Knowing that, we should be able to draw a ray diagram for this, and we kind of started doing it last class, but I want to make sure that everyone understands. One thing that's very, 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 very important here is that you have you have your lenses set up such that their focal lengths are on the same position. All right. So you can see here I have an f1. I'm going to change colors here. I have an f1 of 50 centimeters, and I have an f2 of 10 centimeters, right? And therefore, my distance between them is going to be 60 centimeters, with the focal length at their respective positions. So that's important. That's what you want to have in a telescope. All right. And so let's see what happens when you know you're looking at something that's really far away, and you want to figure out where the image is and how you see that image. I want to point your attention to the fact that my observer there is on the right. So I'm going to go to the easiest one first, and that's the one that goes straight through the lens. Right. So I have a ray coming in like this. And it kind of looks like that. There's your incident, and there's your refracted, right? And you know that the ray that goes through the center of your ray is going to be going straight through. all right? Since you're looking at something that's coming from very far distance, all the rays are parallel. So if I have another ray coming in, it's going to be parallel to the one that I just drew. Okay, well, maybe I could draw it a little bit better. That, right? The rays are coming in parallel, right? And because they're coming in parallel, they're going to meet at the focal point. So now after they've hit the lens, I'm going to go ahead and meet this ray at the focal length. So I'm going to draw just another one here, also parallel, and it's going to go ahead and meet at the focal point. Okay, and you might be asking yourself, why is it coming everywhere along the lens? Well, that's just the way that the telescopes work. So if I want to go back to this image here, no, not this image, but let's find a better one. Where is that? Oh, no, I don't have it. Okay, forget it. The fact that is that the light doesn't necessarily just come from the principal axis. The light can come from anywhere in the field of vision. All right. And in this case, you have an image that's being formed on the focal length. And that makes sense, right? So if I have my equation, 1 over f is equal to 1 over di plus 1 over do. And my do is at infinity, right? So my do is at infinity. And so that expression gets canceled out. I have 1 over infinity, 1 over f is equal to 1 over di. Therefore, di is going to be equal to f. So the image is being formed on the focal length when the object is at infinity. Make sense? Yeah. Now that becomes the object of the second microscope. And so what we can do is I'm going to erase everything that I drew so far, so it's less messy. So here's my image that I got. And so this is going to become the object of my second lens, which is over here. The first ray is, I'm going to draw the focal point on both sides. First ray is parallel to the principal axis, and then through the focal point. Then there's the one through the center. Then there's the one towards the focal point, but this one doesn't really work, so it doesn't have a ray. It goes like this, kind of like that. And what you notice here is that these rays are actually parallel. Redraw it. These three rays, rays 1, 2, 3, they're actually parallel. So where do they converge? At infinity, right? So if they converge at infinity or very far away, then my image that I'm being produced is infinitely big as well, right? And you want that. In a telescope, you want to take this distant, tiny, 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 tiny thing and make it as big as possible, right? So these rays are going to meet at some point at infinity, right? That's perfect, because when they're meet at infinity, you create an image that is infinitely large. And that's really good for what you want. You're using a telescope to be able to magnify something that's really far. So it's going to create a huge image. And now what you're looking at as the observer, right, is an infinitely large image. And for you, that's a lot better than, looking at the star or whatever it is that you're looking at with your naked eye, because now it's infinitely large. The disadvantage of this is that you can't necessarily resolve two images with this kind of telescope. So what I mean by resolve, guys, look outside, look at the fog. You can't even see the building across. It's crazy. That's dispersion, by the way. The fact that we can't see it is referred to. So back to this. Let's say I had two dots really close together. You guys ever do this experiment of science? Did you ever do that experiment where someone pricks you with two sharp objects near each other and then further and further apart? No? Let's do that experiment because I think it's quite cool. Matej, I'm going to use you as an example. Yeah. You're going to get poked. Who has two mechanical pencils? Your mechanical pencil? All right, close your eyes. Stick out your hand. All right. Stick it out flat. Yeah, like that, exactly. All right, now close your eyes. And you're going to tell me with how many pens I'm poking you. One or two. Okay? So it's going to be the first one. One or two. One. Okay, open your eyes. So he had a really good resolution on those pricks. He was able to tell me that there were one or two each time. All right. This is gonna be a little bit more weird. So you're gonna stick out your whole arm, and this time I'm gonna go in the upper part of your arm. Okay, maybe go in the middle so that I can stand my head. Yeah. So pull up your sleeve. All right. Close your eyes. And you're gonna tell me if it's one or two. One. Now I'm gonna. So they're not all ones, by the way. Yeah. Okay. And so now, so your arm back up. Okay, close your eyes. Am I hurting you? No. You might want to get that looked at. All right, so here we go. All right, thank you. Put your pencil in. So the concept of resolution is that that you can determine two distinct objects when they're really close together, right? So let's say you're looking at the binary star system. You have two stars that are really close together. You can't really tell them apart because they kind of blur into one. All right. This kind of telescope doesn't help you with that. It's going to be a big blur, and you're still not going to know. So similar to what happened to his arm, he doesn't have enough sensory receptors on his arm, right, to be able to resolve two really close together pokes. All right. But on his finger, he's got a lot of, because we use our fingers for a lot of sensational stuff, there's a lot more nerve endings on our tip of our fingers. So when I pricked him with two, he was able to determine it on the tip of his finger. But not here, because we don't really feel with our shoulders or with our elbows. Right? And that's everyone. We're laughing at him because he's the one at the front, but everyone's like that. So it's the same kind of thing when it comes to using our telescope, right? So we want to be able to resolve, and that this doesn't really help us at all that much. If I were to ask you on this example what the magnification is on these two, we have a very simple equation for this. So it's just going to be m is equal to the objective divided by the eyepiece, and in this case, that would be just 5, right? So this telescope system provides us a magnification of 5. The reason I got that is 50 centimeters divided by 10 centimeters. Okay. So so it's not an excellent telescope what I have here. If I had a way bigger focal length for my objective, I would have a much bigger magnification, but I don't. However, if I want to have more resolution, all right, and that's the whole purpose of it. I want more resolution. What I need is more light being funneled into my telescope. All right, so the focal lengths aren't going to really matter in this case, and so what I need is a gigantic lens. And did I talk to you guys about the giant lenses a little bit? Yeah, so gigantic lenses are hard to come by, they're hard to manufacture, they're costly to transport, they're easy to break, so they're not very practical. So what they'll do is they'll build like a concave surface, right, and then paint it with reflective material. So you're creating this giant mirror. And using mirrors is kind of similar to using lensing. So what you end up with is what you call a compound telescope or a reflective telescope. And that's kind of what the Hubble telescope is like, right? So you have this big wide opening here, allows a ton of light to come in, right? And the way we get that, how we funnel that light close to our eyes so that we can see all this fantastic images coming from outer space, there's two mirrors reflecting here that are pointing into another mirror here, and they're reflecting it back into the eyepiece. All right, that way we're getting big amount of light funneled down to a small amount of area. All right, and that's what's going to allow us to resolve much more beautiful images. All right, we can't necessarily have this gigantic lenses to be able to capture the light. Yeah. Well, we can't look at it live, but computers can, right? And so a computer, what will happen is they'll, instead of our eye being placed right there, you'll have the computer screen being placed right there. Kind of like a digital camera, right? You take a picture of something and then you look at the picture. So let's say you wanted to look at the remember at the beginning of the fall we went outside, we built these boxes to look at the moon. Are you guys there for that? Not the moon, the eclipse. You guys weren't there for that? Maybe it was the first year. But there was an eclipse. Remember on the first day of school there was an eclipse. Um, so what we can't do is look at that directly with our eyes. What we can do is take a picture of it and look at the picture. Looking at the picture is not going to harm our eyes. And that's the exact same situation on anything that's cosmic, really. Um, and that makes sense because our eyes are also limited to our visible spectrum, right? Our eyes can only see, if I were to go back here, our eyes can only see between this entire light spectrum. Our eyes can see this, right? And the universe doesn't care about what the human eye can see or not see. There is the presence of all of these things in outer space. And we're looking at stuff. We're not only interested in this very narrow range, we're interested in every single range. So what we can design is sensors. So if we have a sensor here that are sensitive to not only visible light, but sensitive to infrared light or UV light or X-ray light or gamma light, right? And so what we can do is we can create these huge, beautiful images with nice resolution. Like this is not what it'll look like if we looked at it with our eyes, but if we were able to see infrared, for example, this is what it would look like, right? And we can see this because we can use sensors that are sensitive to infrared. You guys know what this is? No one's seen one of these before? Not with their naked eye, but a picture of this? What's it called? So this is an N. Yeah, it's a nebula. And there's two kinds of nebulas. They're called planetary nebulas or stellar nebulas. Basically, in the life cycle of a star, right, it first starts off as a planetary nebula, meaning that there's a whole bunch of gas floating around, right? And when their gravitational pull becomes strong enough, because there's so much matter in one area, it collapses. The planetary nebula collapses into a small star, right? And this star grows and grows and grows. And eventually, if you have a really big star, that big star basically goes into it's called a supernova. And when it supernovas, you get a stellar nebula, which is a bigger, much bigger version of a planetary nebula. These are massively impressive. They're super humongous, and there are evidences that they can actually light up the entire sky for a brief moment when this gets formed for the first time. It's really quite impressive if you're interested in astrophysics. The concept of light cycle are really, really, really interesting. Go look into this stuff. Nebulas, they're so cool. So again, there's some more impressive images that you can take from outer space using other sensors outside of the visible spectrum. It's very helpful. We get a large amount of data from non-visible light data, and it doesn't even have to be light data. It could just be radio frequency, right? So you guys know the Voyager space shuttle. The Voyager is a space shuttle that we launched in the 70s that for the first time, a few years ago, for the first time, it was the first man-made object that has left our solar system. All right. So that means that it's beyond Pluto now. It's outside of what we consider to be our solar system, and it's inside what is called interstellar space. First man-made object. It took 30 plus years for it to get there, and it's still on its way. It's traveling at around 30,000 meters per second, and we still get some data from it. It's very, very, very slow to get data from it, but we still do get data from it. And what we get is radio waves. And how we get that data is so we have a dish like this. I'm just going to draw a simplified version. We have a dish like this that has a sensor here, right at the middle, and all the radio signals are coming in like that and being reflected to this one point. So it wouldn't be enough data if we were to receive just one wave at a time and try to interpret that data. What happens is all this wave is being funneled into one point so we can compile the data and get a stronger signal, right? And then we can get that information. So Voyager is sending us information from interstellar space, which is nuts, right? No one human has gone beyond the moon, right? And now we're getting information that that there is stuff that our own things that we've made are outside of our solar system. It's really impressive. Fun fact about the Voyager: they put this golden disc together on it, and they put this on the Voyager. Do you guys ever hear about this golden disc? No. So exactly. So this disk that they put onto the Voyager is basically the instructions on how to use that disk. So it's a regular compact disk that has been engraved with it's engraved on gold, so that it has a very long half-life. So like thousands of years from now, if it ever gets encountered by another living organisms, on the disk physically is engraved instructions on how to build a machine to use the disk and to interpret what's on the disk. So on the surface of it, there is the code that allows you to build the machine, and then there is the I'll show you. It's so cool. All right. So how do I blow this up? It's not a vinyl. It's an actual compact disc. Yeah. All right. So this is what the disc looks like. This is what's engraved, right? So this is all of this. So first of all, there is this kind of universal language that they use to kind of describe everything. So first, you have to understand that this is a language, right? And they made it as simple as possible so that like the most basic form of intelligent life is going to be able to understand it without knowing any English, without knowing anything. Um, well, you have to be a scientist. Here, they have the most simplified representation of a hydrogen atom. All right, so it's got one proton and one electron, and it's being bonded. It's the most simple atom that exists on planet. Here, this is my favorite part. So this is the points of these lines represent other nearby stars, right? And their address in proportion, right? In the right ratios to determine where we are located, where our star is compared to the other stars. So it's an address to our solar system, right? And um, and then, so this is the digital data that you need to be able to identify. So it's kind of like talking in binary. It's the digital data that you need to build the device that's able to read this. And on the disk itself, there's a Michael Jackson song. Yeah. So like that's kind of like our culture or whatever. And this is being sent off into interstellar space for someone to discover this, thousands of years. I find it so comes back to us and we don't know what. Yeah. The what? Nope. What is it? Okay. Not just our planet kind of thing. What's it called? Pioneer plate? Okay, I'll look it up. I'll look it up. Pioneer plate or pioneer plate. All right, let's get back to this. I think that's pretty much it. All right. So that's pretty much it for telescopes. There is a big application to this in the realm of engineering and astrophysics and all that stuff. So keep it in mind if you ever end up in those fields. But now we're going to take a little bit of a right turn and we're going to go to the biology side of this and we're going to talk about the eye. So let's go to PowerPoint 13, and this one is called optometry. Pop quiz. What kind of doctor looks at your eyes? Nope. Why would I ask something so simple? Eye doctor? Anyone know? What is a doctor that looks at your eyes? What? So you have, let's say, a radiologist who looks at, X-rays and things like that. You have a not orthodontist. That's not really a medical doctor, but oncologist who looks at cancer. You have a cardiologist who looks at your heart. You have an orthopedist who looks at your bones. So what is someone who looks at your eyes? It's not a joke. It's an actual term. The joke is in how it's spelled. I'll give you a hint, and I'll answer it for you. It's called an ophthalmologist. All right. Who has seen an ophthalmologist at some point? All right. You should know that what kind of person is looking at your eyes. It's important. Um, how is it spelled? I'll give you a hint. It starts with an O. What's the next letter? O-P-H. Okay, I'm agreeing with this so far. So the word is ophthalmologist. P. This is one of the mind games that this word plays with you. Next. A. Nope. This is another one of those mind games that this word plays with you. Nope. Nope. X. No, just kidding. L. Then it's mologist. Ophthalmology. It's ophthalmology. Yeah. Fun fact, I wanted to be an ophthalmologist when I was in high school, and then I went through the whole health science route in CEGEP, and I went into biochemistry as a stepping stone to get into med school afterwards. And in my undergrad, when I was doing my bachelor's, I took a course called Integrative Neuroscience, and that course kicked my ass so hard. I felt like the most stupid person on the planet, and I was just like, yeah, maybe this is not for me. Maybe people don't want me looking at their eyes if I can't do this. Yeah. That course really sucks. Oh my god. All right. So what we're going to do today is we're going to look at how your eyes work physiologically. Did you guys learn about that term? You know, you're taking a course called physiology, but you know what it means, physiology? How it works, not necessarily just how it works, be more specific, because there's a difference between physiology and pathology. What's physiology and pathology? It's both related to the anatomy, so that's not quite it. Physiology is how something works when it's healthy, and pathology is how something works when it's not healthy. Okay? And so we're going to talk a little bit about the physiology of how the eye works, so how it works when it's healthy. And we're also going to talk about some visual impairments. I'm not talking about like diseases where you have tumors in the eyeballs or anything like that. We're talking about just visual impairments, really common thing. And so we need to know the parts. All right, and we saw a few of these. Um, so really, the important things for us is the pupil, the lens, this thing called the ciliary body, and of course, the vascular fovea. All right. We're going to look at the biology part of this relatively quickly. I don't want to get Madame Patino talk to you guys about this. But what's important for our class is this thing called a lens, right? Which is kind of like the thin lens that you guys use in the lab, that we did all those math problems with. Essentially, there are two muscles attached to the lens, and the muscles are called the ciliary body. There's other names for it, but this is a very common term. And these muscles, and they're not just two actually, it's all around it. It's kind of like a sphincter muscle. And what happens is it can pull on the lens this way. And if the lens is a bit flexible, which it is, you guys saw that upstairs, it's kind of mushy. If you were to pull on the lens, what do you think is going to happen to the lens? It's going to flatten out. It's going to become thinner, right? And if it's thinner, is it going to refract more or refract less? It's going to refract less, right? So there's going to be less refraction when the lens is really thin. So you pull these apart, and the lens becomes thinner. If you relax these muscles, the lens gets compressed and contracted back into its thicker shape, and then does it refract more or less? More. Overall, the refractive index, the N value of the lens is 1.406, right? So it's very close to glass. Glass is 1.5, water is 1.33, so I guess you can say it's between glass and water. So this will relax and contract. Ultimately, what you want, right, is for it to converge light onto this area called the fovea. The fovea is where there's the highest concentration of photoreceptor cells. All right, so that's where your image needs to be formed. If your image is formed there, you're going to see a sharp image. Right? If you were to take something that's written and place it over here, right, and try to read it by looking over there, it's not going to look very sharp. Right? You can't read it. And the reason for that is because your visual acuity is only really good directly where your eyes are pointing to. All right. And so the reason for that is because you have a higher concentration of rods and cones, higher concentration of photoreceptor cells right there. There are still cells here, but they really only serve as the periphery. Okay. And so they don't need to be as resolute. They don't have to be as sharp. Okay. The pupil is the hole in which the light comes in, and we talked about that downstairs. And the iris is what contracts and dilates in order to control the amount of light. Quick side point here. On Monday, well, this Friday actually, when you have class together, I'm going to talk to you guys about pinhole cameras because next week we're going to you guys are going to be developing pictures from your pinhole cameras, which you will have had to have made over the weekend. Okay, not a long or complicated process. Just anticipate having to do something like that over the weekend. Okay. So keep your schedules open. I'm going to talk about it on Friday. If you want to take a heads up and do it earlier, I'm telling you guys now, and you can do it on your own. Just do some research about what you need to put together for a pinhole camera. Just a little bit of a hint: you want the inside of it to be totally black. Okay? All right. Back to this. So you have the light coming in, and it's going to converge. You want that to be the focal point. All right. But the thickness of this will change your lens's focal point. So let's take a look at that a little bit. All right? So I put together this physics kind of information slide for the eyeball. And there's some really important information. Okay? First and foremost is the distance here. Oh my God. This distance here is quite important. This 24 millimeters is the distance between the lens or what we call the surface of the cornea, but this distance is actually quite small. But the distance between the lens and the back where the retina is. Okay. Another thing that's important is this thing here. Okay. So when light is coming in from, let me draw a little. I'll draw a side. If light's coming in from far, the light rays come in parallel, right? And here's your lens and your eyeball, right? You need to converge it. You need to converge these so that the light rays end up on your retina in the back of your eye. Okay? If they don't converge on the eye, at the back of the eye, then you're not seeing a clear image. There's a visual impairment there. Okay? When you're looking at an object that's close, oh my God. Right? If I'm looking at this object that's really close, we're going to call it a dot. This object is going to have diverging light rays coming out of it, right? And so the ones that hit the eye are going to be diverging, and you need to converge the rays to focus on your eye. So you need to do two different things. But at both these situations, you want to focus at the back of the eye, right? So which one needs to converge more? When you're looking at an object far away or when you're looking at an object close? Closer. This one needs to converge more. So if you need to converge more, you need to have a smaller focal point. Right? So your F close, your focal point, when you're looking at close objects, is going to be lower because you need to converge. We need a stronger lens to be able to do that. And for objects that are far away, you need to converge them less. So you have a larger focal point. Okay, you need to refract less for that. The light comes in here, hits your lens, has a refractive index of about 1.406. Though if you go further outwards, the refractive index kind of changes, and that's because of the concentration of the proteins that are in the lens, right? And I'm super oversimplifying it because there is this liquid here, which is called the aqueous humor, right? And the liquid here, which is called the vitreous humor, both of which have their own refractive index of here 1.336, here 1.337. Okay? If this is the lens, and this is the length of the eyeball, 24 millimeters, we can kind of figure out a few things. All right, so let's do a problem. So the question says, what does the focal length of your lens need to be if an object is located 12 meters in front of your eyes, right? So 12 meters is relatively far, let's say, right? And we want to find out what our focal length needs to be. So think about this. I'll give you 2 minutes to think about it, then we'll talk about it together. Try to problem solve this question, all right? Because I only gave you this information, and I'm expecting you to tell me something about this information. So think about it. Let me go back one slide now. If my lens is here, and the back of my eye, where the retina is 2.4 centimeters away, or 24 millimeters away, is that a variable number or a fixed number? That's pretty fixed. I can't really control the size of my eyeballs. Anyone? No, wait. You can't really control the size of your eyeballs. It's going to be slightly different for everyone. This is what it is for the average human that's healthy. And so this distance has to be the image distance. That's it. There's your constant. So now we have some information here because DO is equal to 1200 centimeters. DI has to be equal to 2.4 centimeters. So we can find our focal point. If this number is humongous, and it kind of is, it's not like very big, but it's still pretty big. We're going to expect that our focal point is going to be actually pretty close to 2.4, right? Because if an object is at infinity, the image is formed on the focal point, right? So 1 over 1,200 plus 1 over 2.4 is equal to 1 over f. And so f is going to be equal to, what did you guys get? 2.4, kind of what we were expecting. Okay. And if I go back here, I said that when I look at something far, my focal length is at approximately 2.4, right? And as I'm looking at something further and further and further and further away, and you guys should know this based on your lens lab that's due in a couple of days, as you look at something further away, the image is going to be formed closer and closer to the focal point. Now, what if this wasn't 12 meters? and it was instead 12 centimeters. Now you're looking at an object that's actually pretty close. You ever try looking at your phone 12 centimeters away? It's not very easy, right? And your eyes need to do some kind of gymnastics to be able to resolve it. But the point is that your eye still has to have the flexibility of switching between long and short distance, all right? So let's just do the equation real quick. 1 over 2.4 plus 1 over 1.2, or sorry, 12 rather. Oops. 12 is equal to 1 over f. And f is 2. I want you guys to do something. Everyone pick up your book that you have in front of you. Anything in front of you has writing on it. I want you to bring it both of you down to your face until it's touching your face, and then move it backwards when it's touching your face. You go, it can touch your face. That's right. It can touch your face. All right, and then I want you guys to move backwards until you can read it comfortably, and then stay there. So I'm going to count to 20 seconds. All right, and when my 20 seconds is up, I'm going to point to a word, and you guys are going to try to read that word. Okay? Bob, you should be looking at me right now, looking at your thing. So we count to 20 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Look at the word. All right. So you guys were able to read it. How easily was it? If it was easy for you, put up your hand. All right. That's because you're all young. All right. And what you're going to lose with age is that ability to transition from looking at something close to looking at something far. What your lens just did was it went from being thick to being thin, right? If you look at something close, your lens needed to be thick, you need to contract, you need to convert more light. And in order to look at something far, you need to make your lens thin in order to converge less for it to become fully focused. As you get older, you get something called presbyopia, which means that your lens cannot do that transition as well anymore. You see your parents doing this? Yeah? Yes, I'm all right, that's what that is, okay? The reason is because your parents are losing their ability to change the focus. If I were to do that experiment that you guys did, I would also find it easy, but not as easy as you guys. And I would do it, it would take me, let's say, half a second, whereas you guys was almost pretty much instant. As soon as you looked up at the board, you were able to read that thing, okay? Questions? I have a couple of, now we're going to move away from the physiology and enter more pathology, okay? So what happens if the axial length of your eyeball is elongated? By the way, the axial length is the distance between the lens and the back of your eye. If your lens is elongated, or not your lens, your eyeball is elongated, what's going to happen? So let's try to think about it. William, what do you think? The focal point is going to be what? Yes, be more specific. You're right, but be more specific. That's not what I'm looking for here. So the focal point is not going to be where it's supposed to be. Where is the focal point supposed to be? Where? At the back of your eye. You want the focal point to be at the back of the eye. But let's say you have a lens. Here's your normal lens, healthy, right? And light's coming in, and you focus it to the back of your eye. But now, unhealthy, you have a really long eye. Does your lens know that your eye is now all of a sudden longer? No. Is there anything wrong with your lens? There's nothing wrong with your lens, right? What's wrong is your eyeball, right? And what happens is it's not going to converge. Conversion is fine. Healthy lens, healthy eyeball, unhealthy eyeball. So the image is being the focal point is getting there, and your retina is not getting sharp image because what ends up happening is these rays cross over, right? And an object that's here, instead of it being a sharp object where all the rays converge in one spot, going to get a blurry object, right? Because there's that the light from one object is now being spread out over a distance. So you're going to get blurry vision. Okay. What happens if the axial length is shortened? Where does the image form? Behind the eye, exactly. So if you have a shortened eyeball, the image is going to be formed back here, right? And that's also not good because you want it to form on your retina. What happens if your ciliary muscles become inactive? So ciliary muscles, I'll remind you, are the things that stretch and relax your lens. Your lens, not your eyeball, but your lens. What do you think that might happen? Yeah, so now you have a lens issue and you're not able to focus the lights where it's supposed to be. So these are three very common visual impairments. The first one, you guys know what it's called? A lot of you have this one. Myopia. This one? Reverse myopia. It's called? No, it's not. It's not called that, but it essentially is that. It's called hyperopia or hypermetropia. And this is the one that your parents have. This is presbyopia. Almost everyone gets this. Don't fight it. It's gonna happen. All right. Any questions? So let's talk about that. Myopia is a problem where you have a hard time seeing far things. All right. So another word for myopia is called being nearsighted. And being nearsighted means that you can see things that are near, but not things that are far. All right. So let's see what happens when things that are far. So this is an axial elongation, by the way. So here's myopia is an example of axial elongation. So your eyeball is too long. Here's your lens, your eyeball lens, right? And your eyeball is way too long than it needs to be. And so the image is formed in the middle of your eye, okay? So in this case, is your lens focusing too much or not enough? Too much, exactly. So lens is over converging. Okay? And what you end up getting is blurry vision. For far objects. We're going to talk about that. So you get blurry vision for far objects when you have this issue. Okay. Let's talk about hyperopia. Sorry, I went too fast. I'll give you guys a second. Hyperopia is when you have axial shortening. So your eyeball is too small, too short. Axial shortening. You have an object that's close. By the way, this is far-sighted, which means that you can see far things but not close things. See far things but not close things. So I have an object that's really close, that's shooting some diverging rays towards your eyeball, and your lens needs to focus them, but your lens needs too much time to focus because your eyeball is too short. So it gets converged to the back. Okay? So is your lens converging enough? Not enough. Not enough. So lens is under converging. I really, really, really want to emphasize one thing here, okay, guys? These two, myopia and hyperopia, they are not a disease of the lens. Your lenses are normal. Okay, it's the shape of the eyeball that's not fitting with your lens. Okay, the lenses are working normally. Okay? I wrote that it's under converging, but it's just under converging in the context of your small eyeball. Yeah. You can, yeah, because presbyopia is something that comes with age, and if you're someone who has myopia throughout your life, hyperopia throughout your life, and you develop, or sorry, you have myopia throughout your life, and you develop presbyopia, then you have both types of visual impairment. No, because one of them is your eyes too long, the other one's your eyes too short. Presbyopia, this is the age-related one. It's age-related. And it is a stiffening of the lens. The lens becomes too stiff. It can't do that elastic motion that you guys did before. You guys went from looking at something close to looking at something far. They can't do that properly. In fact, the lens actually hardens in such a way that you become farsighted. All right. So if you're farsighted, is your lens stiffening at an elongated position or at a contracted position? Elongated, right? Because you're able to see far objects but not close objects. So stiffening of the lens at the elongated position. Okay. So what ends up happening is you have an elongated lens. You're looking at an object that's close. And if it's elongated, it's not bending light enough. So therefore, it's going to converge behind the eyeball, even though you have a normal sized eyeball. Yeah. If you have presbyopia, you can only focus on things that are far. Oh, you can't. No. And in fact, if you looked at, let's look here. Well, yeah, like let's say you're doing what Andre is doing, right? If I'm looking at Hugo right now, my hands are super blurry. If I'm looking at my hand, then the whole class is blurry. You can't focus on both of the same time. It makes an image for each dot. So like remember I talked about an object being made up of many dots? That's what it is. You good? There's some terms that I need you guys to understand, and they're called the near point and the far point. So the near point is the closest distance that someone who is farsighted can see clearly without corrective lenses. Is anyone here farsighted? Farsighted is hyperopia. If you're farsighted, that means you can see things that are far, but not things that are close, right? And so there's a definition of a point where an object goes from being considered to be too far, or sorry, far, comfortably far enough for you to be able to see, to the point where you can't see anymore. Yeah? Why is that more rare than you? I don't know why. I imagine they're all genetic related, so it could be just the allelic frequency of the mutation. So, for example, let's say Hugo was farsighted, okay? And for him, it's easy to read things that are far, right? You're farsighted now, right? I'm pretending, right? You're farsighted, right? And that means you can read things that are far, okay? But you cannot read it when it gets closer to you. Yeah, beautiful, isn't it? It's a drawing of beauty. And then there's a point where so he can see this beautifully, right? And I bring it closer and closer and closer. Now his visual impairment call this near point. That distance from where it becomes comfortable to read to uncomfortable to read, that point is this near point. Okay? Similarly, so I'm guessing that you're actually in this level. I'm just totally blind. So if you take off your glasses, then you read this word. Yeah. This is your far point. Okay? And your far point is the point where someone who's nearsighted can see it comfortably to the point where they cannot see it comfortably anymore. Okay? So you can easily measure what your far point and your near point. All right? All right, we need that information because what we're about to do is shame all of the opticians or optometrists that you guys ever go to for charging you any money whatsoever. Because this stuff is easy peasy. You can prescribe your own glasses after you go through this math. All right. Before that, let's talk about some corrective measures. All right. We're going to go over this part pretty quickly because it's very intuitive. Here's your myopic eye. Your myopic eye is too long, so let me just exaggerate this a little bit. Your myopic eye is too long, right? And normally, image is converging there, but what you need to do is you need to wear glasses to converge it further back. All right. So normally the image is being formed there. We need to form it further back. Light rays are coming in this way, like that, from a far away distance. And so now they're going to hit your glasses. What kind of glasses do you think you need? Converging or diverging in order for it to converge less? Kind of giving away the answer. You need to have diverging glasses. So you're going to have, I'm going to simplify this and just show you an eye concave lens. Now what's going to happen is the light rays are going to come here. They're going to diverge, but then they're going to converge again. And now this time, because you've diverged them a little bit, giving your eyeball more time to converge them, and so they're going to converge in the back of your eye. Yeah. Did you ever hear your eyes are squares or something like that? It's made up. When you play too many video games, that's good. But no, what happens is if you look at a book for too long, or if you look at something at the same distance for too long, your lens kind of stays in that position because it's called adaptation, and you've adapted your lens to look at close object for a long period of time. So when you look far, your eye takes a few seconds to adjust to now looking at far objects. Yeah, so it's not video game or screen time necessarily, it's distance from your eye. All right. For the other one, for hyperopia and presbyopia, your light rays normally converge too much, right? Converge not enough, rather. Right. So if they converge not enough, you have an object that's close that has this. What kind of lens do you need to put in order to converge it for you a little bit before your lens can converge it? Yeah, you need to put on a converging lens, and that's also quite intuitive. So you put on a converging lens, and so this bends it a little bit before it hits your eye, so that your eyeball that can't normally converge it enough is now having an easier time converging, and your object and your image ends up on your retina. Make sense? All right. When you go to the optometrist, what they're going to do is they're going to give you a prescription. Hugo, what's your your glasses prescription? You have no idea? Someone who does? Safira? No, me? No. What about you, Shah? What's your prescription? Okay, Olivia, yours is minus 14? 2? 2 and 1. Plus 2 or minus 2? Plus. And yours is? Minus 4. So the plus and the minus determine if it's a converging or diverging lens. Converging is plus, diverging is minus. All right? So if you're at a minus 1 and plus 1 and a plus 2, that means that your lens power is 1 diopter and 2 diopter. Yours is minus 4 diopters. All right, and that's the unit that you use to look at lens power. This is how simple it is, guys. It's 1 divided by the focal length. Duh. That's it, right? You look at your glasses, right? Whatever power you have. So Olivier said his lens power is -4. So his focal length is going to be 1 over p is equal to 1 over -4, and it's measured in meters. It's going to give you an answer in meters, right? This is a diopter. It's going to give you an answer here. So you have 0.25 meters. The focal point of Olivier's glasses are 0.25 meters. Okay. If you know the focal point of what you need, which is what we're going to calculate next, you know exactly which prescription you're going to need to go buy. All right. So in Ibrahim's case, if he's +1, then his focal length is going to be 1 in one eye and 0.5 meters in the other eye. Okay. So far, so good. Got a question for you guys. Which of the following two people has a greater visual impairment? A person who has a far point of 10 meters or a person who has a far point of 5 meters? 5? Yeah, 5. Because a far point is when someone who is nearsighted, when can they not longer see anymore? So if they see perfectly up until 10 meters, that's great. But if they can only see up until 5 meters, that's not as great. Okay? All right. This is a hard question at first, but you'll see it's actually very, 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 very simple. A patient has a near point of 0.75 meters, okay? And wants to get glasses so he can read comfortably from a distance of 0.25 meters. So in general, convention is when you read a book, you should have it at 25 centimeters away from it. All right, so that's where you want to be able to read comfortably. So this person is obviously visually impaired because they have a near point of 75 centimeters. What does the focal point of the person's glasses need to be in order to correct it? I'm not going to say it. Talk about it amongst yourselves for 2 minutes, and we'll talk about this together. Okay? Try to figure out what it could be.
The distance of the image has to be 0.25. You know the distance of the distance of 0.5 is the distance of the image is the back of the eye. But we don't know because this is but he has a near point of 0.75. Yeah. But with the near point you could find the it was 0.25 exactly. That's distance. Was DO 0.25, right?
All right. So I'm glad of the way you discussed it. And I'm going to add one piece of information that's going to make this crystal clear. No pun intended. This person can read things if they were at 0.75 meters, right? So what you want to do is place the image at 0. You want some glasses that are going to place the image where it's comfortable for you to read. So this person is saying that whatever it is at 75 centimeters, it's comfortable for me to read it, all right? So you have your object that's physically at 25 centimeters, right? But you want the image to be at 75 centimeters because that's where it's comfortable for you. So knowing that, what are you going to do? We don't even care what the eyeball is doing at this point. We just want the image to be at 0.75 centimeters away from us. You want the image to be at 75 centimeters because that's where it's comfortable for you. So that's your image. So in this case, my distance of the object is going to be 0.25. I want my image distance to be 0.75. Right? If I want my image to be at 0.75, what's going to be my focal length? And what's the units here? Okay. So easy as that. My focal length for my glasses should be 0.1875. The only information that you needed here about this person is their near point. Yeah, their near point. You know their near point, you can calculate what their focal length needs to be. If you calculate what their focal length is, what is their power? Let's figure out what the power of their lens needs to be. How much? Positive or negative? So the power of their lens should be positive 5.3. Units is diopter. Before you're blind or before you're considered to be textbook blind? I think it's 8. I'm not sure. I'm not sure though. Like legally blind in the sense that you're not allowed to drive, kind of. So if I knew what my near point was, right, I could calculate what my prescription needs to be. This is what you're paying your optometrist for, folks. It's not that complicated. Now let's demystify this whole optometry thing a little bit more. Not to crap on them, by the way. They're just, if any of your parents are optometrists, just maybe they're not as tired as they say they are at the end of the day. No, I'm kidding. Dealing with stupid people, it makes you super tired, by the way. If you're a person who is dealing with patients or customers, at the end of the day, you've dealt with so many dumb people, you just want to lie down. That's tiring on its own, all right? Let's talk about lens making, because that's an important aspect of optometry. Is that, okay, once you know the prescription, the next step is to make that lens. That part is not as hard, not as easy as making the prescription. So there is this equation here called the lens maker's equation, and this makes your job a little bit easier. The equation is 1 over f, so f is a focal point, right? Is multiplied by the refractive index of the material. So if you're using glass, for example, it's 1.5. If you're making diamond glasses, your refractive index is 2.4. And this 1 here actually represents the refractive index of air, right? So if you're an aquatic animal and you want glasses to see underwater because your fish is myopic or whatever, you're going to use the refractive index of the material of the water instead of air. And here, R1 and R2, that's the radius of curvature of each side of your lens. Okay, so let's do some examples of that because that's the tricky part of it. Okay, on my first example here, I have a lens, and you can see the are different. Okay? First thing that we need to define is what's R1 and what's R2. R1 is the radius of curvature that the lens hits first, that the rays hit first. All right. So the rays are coming in this way, they're going to hit this surface first. So that's going to be R1. How do I find out the radius of curvature of R1? Well, let's look at this. I don't know if you guys can see it from where you are, but this is a part of a circle. And this is a part of a circle. See that? And this overlapping region in between, that's your length. Okay? So is this going to hit the rays coming in? Is it going to hit this circle first, this big circle, or this small circle? It's going to hit the big circle first. So there's your R1. All right. And this one here, the second side, is going to be your R2. You guys follow me? Okay. So that means the eye is somewhere here. All right. And it's important that we define the direction of where the eye is. So in both cases, the eye is going to be on that side. Okay? Now, the second thing that's important here, so we've established what R1 and R2 are. The second thing we need to establish is whether they're positive or negative. Makes a big difference. All right? The convention is if they're curving away from the eye, then it's considered to be positive. If they're curving towards the eye, then it's considered negative. So let's write that down so we don't forget. R is positive when curving towards the eye. Sorry, curving away from the eye. Is it at the bottom? Perfect. I don't need to write it. It's written here. Okay? Now, if my eye is over here, you guys are going to do this one for me, okay? So this one's coming in is, there's a radius of curvature here. And there's a radius of curvature here. So is this one going to hit the small circle or the big circle first? Small one, so that's going to be considered your R1. Is R1 curved towards your eye or away from your eye? Towards. If it's towards, is it positive or negative? Negative. So that's going to be a negative radius of curvature for that one. How about this one? Is it curving towards your eye or away from your eye? Away, right? So look, it's going away from your eyes over there, it's going away and then coming back. That one's going to be a positive radius of curvature. Okay, it's the opposite of this one. Make sense? All right. All right. Now is not the right time for this to not work. It's the best time for this to not work. We're almost done. Over here, there's some examples for you to practice with. I don't want to go over them with you now because when you're studying for the test, I think this is really good. This is really good practice. Essentially, what you need to know though is that if it's flat, it has a radius of curvature of infinity. Okay, so flat means that r is equal to infinity. Okay, so that we don't really care about that. So use this to practice when you're talking about tests. I have one example here. There's only one mistake here that I need to correct, is that here it says R2 and here it should say R1. Okay. I'm asking you guys, and this is the last slide, so after this we're done. I'm asking you, what is the focal point of this person's back? Notice that the eye here is on the right. I'm going to remind you the equation is 1 over f equal to n minus 1 multiplied by 1 over r1 minus 1 over r2. Okay. Somehow I feel every time we're in this class, you guys are down for pizza, like every Wednesday. Minus what? All right. We're not done yet. Give me a second. So the glasses here have a focal point of minus 48 centimeters, or I can say 0.48 meters, and I can calculate the power of the lens, right? The power of the lens is 1 over 0.48. In this case, it's going to be roughly minus 2. That's not what I want to talk to you guys about. Look at this lens. Light is coming in. Light is coming in here. If we were to ignore the second surface of this lens, is it hitting a converging lens or a diverging lens? This is part of a, let's say this is a half of a biconvex lens, right? So this part's convex, it's converging, right? And when it's coming out, it's what kind of lens? Diverging or converging? Diverging. Okay, but now we need to figure out, is this overall a converging lens or diverging lens? We said overall, it's a diverging lens, that's why it's negative, right? So but look at this. This one is a wider turn, so it's got a bigger radius of curvature, right? It does not bend light as much as this one, who has a steeper radius of curvature. So the more rounded the lens is, the more refractive it is, right? So this one is more rounded. The diverging part is more rounded than the converging part, right? So overall, this is going to be a diverging lens, right? So if it's a diverging lens, are you going to be far-sighted or nearsighted when you're using this? Nearsighted? Nearsighted. All right. Thank you very much. See you guys on Friday. Don't forget, think about those pinhole cameras, please. It can be corrected with This one is the most current away from is positive. No, bilingualism is an ongoing evaluation.
Okay, so like I can do my research questions.
But overall, I need to know that you have things. If I look in your folder, for example, is your logbook in English? Is your blog in English or in French? Is your CV in English or in French? Is your president in English or in French? Are your communications with me in English or in French? Your documents, everything. Eventually, I'm not gonna like it because it's a lot of work. But yeah, eventually. This is not a full lab report, so you don't need to.
Can it just be like, are you asking for info? Or can it just be like,
A logbook is literally everything. You just had this conversation with me, now it's gonna go in the logbook.
oh yeah?
Yeah, it's like that. It's like a diary of everything. Yeah, for sure. Very brief. Yeah, you say what is it?
This date,
Yeah, absolutely.
do I say like, by this date, I want to be.
Yeah, you can talk like you can also project for the future. It doesn't have to be what's already happened. Yeah, like how much time you spent on it. We had this 5 minute conversation. You spent 2 hours going to go get your vaccines or whatever. You spent 3 hours on the phone with the guy organizing your trip. You spent the 40 minutes. Okay. So that will go in your logbook. I paid today. Cost me a fortune. Yep. Yeah. So if you need to tell me about your experiment, your hypothesized experiment, I should know what you're going to do. Yep. Maybe because it's more bio-intensive. It's always cool when you can take the theory and apply it to something
Yeah,
so
exactly.
tangible.
Because we went to some high school, but not like as like depth.
Yeah.
I see, Cash.
See you Friday.
Yeah. See.